So lesson 6, explosions. You may or may not want your green sheet out, but you might have these equations memorized because we're going to be using momentum equals mass times velocity and the law of conservation momentum. It says this: a rifle bullet leaves the muzzle with a velocity of that. If the rifle is held very loosely, with what velocity will it recoil? You might recall during our forces unit when I was teaching you that forces come in pairs, Newton's third, I showed you a video clip of an elephant gun being fired and the recoil being really, really tremendous. So it will recoil. This is a consequence of Newton's third law, except, Oliver, what's example 1 wanting me to find? Velocity. Okay, that's a bit of a hint as an approach. Is there more than one object in this question? I'm seeing a bullet and a rifle. Is there more than one object in this question? Yes. Is there an explosion? Yes. This is a job for conservation of momentum. Is there a collision or an explosion? Is there a jeune? Conservation of momentum. But other hints, 2 objects. Okay, so I'm going to start out exactly the same way I started earlier. My abbreviated version of writing the law of conservation of momentum is that. How do I read that out loud? The total initial momentum must equal the total final momentum. The sum of all the initial momentum equals the sum of all the final momentum. Before you pull the trigger, what's moving? The bullet, the rifle, both, or neither? It's meant to be stupidly obvious. Neither. So then, what's my initial momentum? Yeah, you know what my final momentum is going to be? Yeah, it is going to be 0. Now, look up. Don't write this down. Don't write this down. I'm not going to write down 0 equals 0. I am going to say my initial momentum is 0, and that's usually what I mean by an explosion. An explosion is a situation where you start out with no momentum, which means, Christy, we're going to end with no momentum. Bang! The gun goes off. See, you did better. After we pull the trigger, what's moving? The bullet, the rifle, both, or neither? I think both. Stuck together or separate? Unless something's gone horribly wrong, very separate. So I'm going to have momentum, you know what? B for bullet plus momentum R for rifle. Pick letters that make sense. You could have called them both final, but since they're the only ones that showed up, I got lazy and didn't call them initial or final because that's it. Momentum is what times what? Sierra, you're right. So I'm going to replace, the 0 drops down, it's going to be mass of the bullet, velocity of the bullet, plus mass of the rifle, velocity of the rifle. Now, Oliver, you said it wants us to find the velocity, and you are correct. What does it want me to find? The velocity of the bullet or the velocity of the rifle? I think I have the answer for you already for the bullet. What does it want me to find? The velocity of the bullet? Huh? The rifle. Because if the rifle is, with what velocity will it, that it refers to that rifle, because that's the last noun referred to in that sentence. Your English teacher has a name for that. I can't remember what it's called. Is it a gerund? I don't know. Anyways. My English grammar is no longer more gooder, right? What am I trying to find? Say it again. Rifle. The rifle what? Velocity. Which I think is that one there. Okay, how am I going to get that by itself? I'll minus that to that side. What's 0 minus MBVB? I think just, correct me if I'm wrong, negative MBVB. Is that okay? Oliver, how will I get the velocity of the rifle completely by itself? How will I move this M over? What's the M doing to the V? Adding, subtracting, multiplying, or dividing? So I'll move it over by? Okay. Now, what's the significance of this negative? If the bullet goes forward, the rifle recoils backward. If the bullet went north, the rifle must go south. If the bullet goes west, the rifle must go east. They don't go in the same direction. And that is how we are able to keep an initial momentum of 0 and a final momentum of 0. Oliver, I've scrolled down. You're going to have to give me the numbers. Negative. What was the mass of the bullet? MB. I must have told you. 0.0. I didn't hear you.
60.
Like that? Is that right? Oh, there he goes. Yep. How many grams is that, by the way? 6? 60 or 600? How many grams is that? Because I might give you the mass in grams. No one? Okay, that's 60 grams because there's 1,000 grams in a kilogram. So just, okay. Oliver, velocity, VB. Velocity of the bullet? Yep.
6.0
Keep going.
times 10 to 2 miles per second.
Which I think is 600 and meters per second, you said, yes?
Yeah.
Miles? What do you think you are in the States? Jeez. And MR, mass of the rifle.
3.0.
I think I can do this in my head, maybe. Because 600 divided by 3 is 200. So it's going to be 200. 1.2 or 0.12? Double check. Negative. Sorry? Negative 12? Is it? Okay. I was off by a decimal. Meters per second. Which is pretty fast. And I made these numbers up on purpose. This is pretty close to what you saw that elephant gun video doing, where you saw the rifle recoiling pretty fast and people couldn't hold on to it very good. But this is an example of an explosion. Your initial velocity, sorry, your initial momentum was 0. Your final momentum is still 0 because you've got one positive, one negative. I like this question, I like this question, I like this question. And again, what's the significance of the negative in the opposite direction of the bullet? Did I give you a direction for the bullet, north, east, southwest, or anything like that? No, if I had, you would have to then adjust the direction. I used to work at a summer camp, and I was a canoe instructor. And I would see people get out of the canoe. I got to pause the video and act it out as follows. I used to just laugh. Sitting on a canoe, floating on the water next to a dock. He decides to stand up and step out of the canoe and onto the dock. Why does Spencer get wet? Since P initial, I need to make that a subscript. I think I can. Is... Well, you know what, Mr. Let's use math. Equals 0. Oh, ha! It thinks that's pi. Cool. I just learned something new. P final has to equal 0. Yes? Because momentum is conserved. You can't magically get momentum from somewhere else. This is a closed system. If Spencer steps left, canoe must move, fill in the gap, has to. Splash. How do you get out of canoe? I'll show you. Pause the video. Dope. You may have tried this in an ice rink if you've been skating with friends, where you go right towards each other, you push your hands against each other, and then you both push away as hard as you can to see how far backwards you'll slide. Sierra's looking, I never thought of that. I need to try this. Well, there you go. Okay, so a 45-kilogram boy and a 60-kilogram girl are standing in the middle of the frozen pond. The boy gives the girl a push as shown, and she moves off with a speed of 2.4. What velocity does the boy move off with? Thought experiment. Is the boy going to be moving faster, slower, or the same speed as the girl? How do you know? If I look up, change the question to this. What velocity will the boy move off with? 2.4. So now let me ask you the question. Will the boy be moving slower, faster, or the same speed? Not the same speed. So will the boy be moving slower or faster than the girl? Why faster? You're right. Huh? Can you use physics terms? Maybe a word smaller. They're both going to have the same momentum, but opposite directions. How do I know? What's their momentum before they start to push? 0. So what must their momentum be afterwards? Still. And the only way that can occur is if they're equal and opposite. But if the girl has a bigger mass, the boy will have a bigger velocity. So I'm already telling you right now the answer must be bigger than 2.4. You okay with that? Okay. Is this a collision? Well, it's an explosion. It's a slow explosion, but is there more than one object? Are there two objects? Is our initial momentum 0? This is an explosion. So I'm going to start out again by saying, wait. Let's see if we can take a bit of a shortcut here. So I will write out the sum of all the initial momentum equals the sum of all the final momentum to let myself know I'm solving this with conservation momentum. Chloe, what's the initial momentum of everything if we start out at rest? So I'm going to take a bit of a shortcut and do that. Momentum is what times what? So on the previous question with the rifle, I went PB and PR, and then I went to mass times velocity. Can I skip this step right here and go straight to the equation? I think we can. So I'm going to use, how about G for girl and B for boy? So it's going to be mass of the girl, velocity of the girl, and mass of the boy, velocity of the boy. Chloe, what am I trying to find here?
Velocity of the boy.
How would I get that by itself?
Divide.
Not yet.
Subtract and figure out.
Move mg, vg over by making it negative first, and then, so if I hear you correctly, and I think I do finally, you're telling me the velocity of the boy is going to be the opposite, negative, mass girl, velocity girl divided by mass boy. Mass girl, 60, 2.4 divided by 45. I might be able to do this in my head because 60 over 45 is 3 over 2. So it's going to be 3 times 1. Is it negative 3.6? Double check me. 3.2? 3.2. Yes, sorry. Is it negative 3.2? Forgot to carry a 1. What's the significance of the negative? If in our picture it looks like the girl is moving left, the boy is moving to the right. So let's even say equals 3.2 meters per second. I'll do that because the picture clearly gave me some directions. Okay, cool. Tristan, what's B asking me to find? What's another word for impulse, folks? So I'm going to start out by writing this. Now I have all these tools at my disposal. I could go force times time. Wait a minute. Has this question mentioned a force in newtons or a time in seconds anywhere so far? No. What did I find, Tristan, in part A? A final velocity? You know what? I think I'm going to try seeing if I can do impulse by going mv final minus mv initial. Oh, Tristan, what was the initial velocity of the boy? Yeah, you do. Look at, yes. So I can do that whole thing. Yes. So the impulse that the boy experiences is going to be m 45 negative 3.2 because that's the numerical value that we got for the velocity, which is what? I guess in this question, left is positive and right is negative. Okay. Which is what? Negative units. You could either say Newton seconds or you could say kilogram meters per second. If I asked you for a direction, I would say 144 kilogram meters per second. The boy gained momentum to the right. What's the impulse of the girl? You should know the answer already. 144. Direction? Left. How about, I'm going to call for part B, I'll put a boy there, and I'll put a G there. 144 kilogram meters per second left. That's the law of conservation momentum if you break it down into its individual steps. Whatever impulse one gains, the other loses. If the push lasted for 0.25 seconds, with what average force did the boy push the girl? Now, it is true that I have a time and a V final and a V initial and F equals MA. But I can take the impulse equation and do this in one step. I can. Dylan, is there an impulse equation that has force in it?
Yeah.
Could you get the F by itself? Yep. And they want the force that the boy exerts on the girl. What direction is the girl getting pushed? Look at the picture. So I'm not going to worry about negatives and positives. I'm just going to say, I already know the direction. What was it? So I'm not going to put in negatives and positives here. Left. Because the impulse is 144. The time is 0.25. $576? Is that right? Newtons, and if they want a direction, left. I usually put an at symbol after Newtons because otherwise I might think that's north-left because we are doing directions. Habit. Have I taught you anything new yet? I hope not. What's an explosion? Yeah, your initial momentum is 0. Example 4, this is also an explosion, but here we're already moving. A space capsule consists of a 2,500 kilogram main capsule and then a 1,500 kilogram probe. Suppose the capsule is traveling at 120 meters per second when an explosion occurs between the capsule and the probe. After the explosion, the probe moves forward at 280 meters per second. Cool. Cool. Christy, what's A want me to find? Of what? You know what? If I draw this on the picture, I think V equals question mark. Yeah? Let's make some predictions. See the nose cone part here, the probe? Christy, did it speed up or slow down? Did it gain momentum or lose momentum then? It gained. So what can we say about the capsule? I think it's going to lose momentum because momentum is conserved. So do you think the capsule is going to speed up or slow down? I think slow down. Gonna make it cool? Okay. In other words, Christy, if I get an answer bigger than 120, I'm going to get nervous. Okay? Are there two objects? Is this an explosion? This is a job for conservation of momentum. So I'll start out by writing the sum of all the initial momentum equals the sum of all the final momentum. Before the explosion, what's moving? How about we use C for capsule, P for probe. You could use mass A and mass B, but let's use words that make sense. Is that okay? Before the explosion, Christy, what's moving? The capsule, the probe, both or neither? Stuck together or separate? Ah, good. So I'm going to... Momentum is what times what? I'm going to try and skip a step if I can, and I'm going to say, so mass of the probe plus mass of the capsule, V initial. That's what's going on before. Is that all right? Boom! There's an explosion. After the explosion, what's moving? The capsule, the probe, both or neither? Both. Stuck together or separate? Good. So we're going to have mass of the capsule, V capsule, plus mass of the probe, V probe. And both of these are finals. What did you say we're trying to find? Which one? I got them all over the place. Final or initial? Mm-hmm. Yes? A little too obvious, right? So we're trying to get that by itself. Okay. Oh, folks, how will I move this over? Subtract. And then divide by the m there. And I'm running out of room, so I'm going to have to write a little small here, but I think I can fit this in. So you're telling me MP plus MC V initial just drops down like a domino. I'm going to subtract MP V P P P, Mr. Dewick, P final, and divide by MC. That's going to be VC final. We okay with that? I hope. I hope. I'll scroll up so you can see a bit better. Okay, Christy, I've scrolled up, so you'll have to read the numbers to me in just a second. And I'm running out of room, so I'm going to go over here. And I'm going to say, all right, V capsule final is bracket mass of the probe. Christy. Mass of the capsule. 4,000. Is that right, folks? People nodding? Yes? Okay. V initial. I think it's in the picture. I hope. I hope. Yep. Plus, Mr. Dewick. How about I read carefully? It's minus, yes? Mass of the probe, you said, was 1,500? V final of the probe? Now we pause. Folks, is there a direction change that we have to be aware of at all or not? No? So we're still okay? Was the initial initial velocity was forward and this velocity is forward? If there was, I'd have to include that. So what'd you say it was, 280? Divided by mass of the capsule, 4,000. Is there a fraction? Brackets around the top. Hmm. 1,500 plus 4,000. Oh boy. Oh well. Times 120 minus 1,500 times 280, and then divide that by 4,000. Do you get 60? Am I wrong? What'd you get, Hannah? Okay.
Because you put this, the mass of, yeah, you put the 4,000 is the mass of the
Oh. So when I kept asking, is that right? So it's not 4,000. Okay, mass of the capsule. What's the mass of the capsule? Not the probe, just the cap. Ah! Okay. We won't make that mistake again, right? Thankfully, on my calculator, I can backspace and edit. So you're telling me this is supposed to be, I thought that seemed heavy. And then divided by 2,500. 24? Positive or negative? So the capsule has slowed down, but is still traveling, still coasting forwards. Maggie, what's B want me to find? Magnitude just means size. That's not what it wants me to find. Keep reading. Find a physics word. Impulse. The reason I said magnitude is I'm saying don't worry about a direction because I didn't give you enough to tell me north, south, east, or west. So magnitude just means the size of the impulse. Oh, change of momentum. Let's write that down. Am I going to use force times time, or am I going to use mv final minus mv initial here? How do you know? I see several velocities. Okay, so it's going to be m probe v probe final minus m probe v probe initial. Mass of the probe is 1,500. VP final was 280 minus 1,500 times 120. What is the impulse of the probe? You get 240,000 kilogram meters per second or Newton seconds. Do we get a positive or negative answer? Positive. Are you positive? Okay, and since momentum is mass times velocity, what changed for the probe? Did its mass change? No. Velocity changed. Okay. What's the magnitude of the impulse given to the capsule? Cole. I thought you were the one that gave me the answer to this one last time for the rifle question, or the girl pushing question, didn't you? What's the impulse given to the capsule? Cole, what's the impulse given to the probe from part B?
24,000.
240,000?
Yeah, maybe.
Yeah?
Yeah.
So if the probe gained 240,000, finish the sentence, folks. The capsule. And if you want to, Christian, you could go MV final minus MV initial for the capsule, and you will get that number. Because the law of conservation momentum works, no matter which way you use it. Almost done. Mountain climbers use nylon safety ropes because nylon has a tendency to stretch under stress. Why would mountain climbers want the rope to stretch? Yeah. Pardon me? What does increasing time do? Because you're still stuck with the same impulse. If you fall, what do you want your final velocity to be at the end of the rope? More specific, exactly as a number, what do you want your final velocity to be at the end of the rope after you fall? You want it to eventually be 0. Your initial velocity when the rope starts to bring you to a stop depends on how far you fall, and I can't calculate that, but I'm stuck with that 0. Okay, if I can bump up time, I can lower the jerk that the rope exerts around my torso. Maybe I'll crack a rib instead of break a rib or puncture a lung, but I'll survive. It's the same idea as crumple zones. Yeah? Okay. Why does conservation momentum explain why it's so difficult for firefighters to hold hoses that are ejecting large amounts of water at high speed? Anybody here in the fire academy? Anybody here ever use a fire hose? On full?
Yeah.
Solo or with more than one human?
So,
Solo? Is it easy? Why?
it moves around a lot.
Why?
Happy.
It's not just the mass, because you could. It's not that heavy. I could give you that same mass as a weight, and you'd be. Well, this is awkward, but I can deal with it. In fact, you know what? It's about, in terms of mass, it's about the same as a small child, and you've carried kids around before, piggyback or for fun or whatever. Pardon me? It's not heavier. I'm picking my words carefully. It's not a mass issue. It's a force issue. When you turn the hose on, this is very similar to the rifle question. When you turn the hose on, what's the momentum of the water and you? right away before we start. What must the final momentum be then? So if the water has a forwards momentum, what's the hose going to want to do? It's going to want to recoil. And what you're thinking of as heavy, actually, you are having to exert a force to cancel out the recoiling force. In our impulse equation of F delta T, you are applying the F. Oh, and since the water is moving out fast enough that there's not much of a delta T, it's a big force. It is. But it's not a heavy mass down to the ground. It's a weird, awkward at an angle mass as well, much more than the heavy mass down to the ground. If you actually put a fire hose full of water on a scale and just took the mass, it's not that big. When the water starts to move, in other words, when the hose is shut off, try it if you're ever around a fire hose again. When it's shut off but still full of water, pick it up. You'll find it's got some mass, it's got oomph, but it's not like you're going crazy with it. It's when it turns on, now you have a momentum question. Emma's looking at me skeptically. Okay, having used a fire hose, pardon me? I think you're confusing downwards gravitational force with the force required to hold it in place. So, do you understand the answer to example 6? I don't want to write a paragraph. P initial equals, did it again, 0. So P final equals 0. Hose wants to recoil. Fighter exerts force, I'll abbreviate force with the word F, to prevent this. If you open the water up even more so the water flows faster, what happens to the amount of time that it's in your hose? Smaller or bigger? Smaller, so what must happen to the F? Good. See? Oh, yeah. Now, again, if you've ever used a fire hose, you've kind of figured this out, but here's the physics of why. Okay? Last question. The diagram below shows 2 pop cans of unequal mass initially at rest. If I was a good physics student, I would probably underline the phrase at rest. An explosive charge is detonated between them. Boom! And the cans fly apart. What can you tell me about their velocities after the explosion? Are they identical? When would they be identical if both cans had the same mass? Which one's moving faster? The smaller mass or the bigger mass? Smaller mass? How many times faster exactly? Smaller can's going to go twice as fast because the bigger can has twice the mass and they both get the same impulse. And now what you're starting to see, now this is only with 2 particles. When someone like the RCMP or the FBI are investigating in real life explosions and bombs, they're literally finding where all the pieces landed. You can from that figure out fairly accurately how fast they were leaving, which when you work your way backwards, you can then figure out how much momentum was stored in your explosive, and you can pretty categorically determine what the type of explosive was. It's just way yuckier when you have more than 2 masses, and when they're not in a nice straight line, you have to use vector mathematics. But Physics 12, we do it with 3 pieces, and then we say we could do it with 50. It would just take us a few hours, or we'd get some software to do it. So it's very doable. So what can be said about their velocities after the explosion? 2m can is moving, you know what, let's say this. Sure, 2m can is moving half as fast as m can. You know what, I should have written the 2m can move half as fast as m can, because that wouldn't be confusing at all, would it? No? Okay. Can I? Shut up. Prove it. Now, you could do this by making up numbers. You could say, I'll let m be 2. Then 2m is 4. and you could make up a velocity and all. Let's see if we can just prove it mathematically. Before the explosion, what's the momentum? And then momentum is what times what? So I'm going to have this mv plus 2m. Oh, these v's aren't the same. I'm going to call this v1. I'll call the 2m v2. The 2 is for 2m. Let's get v2 by itself. How? Minus that over. I'll get negative m v1. How would I get the v2 by itself? What will I do with this 2 and this m? Sierra, is there an m on top of the fraction on the left? Is there an m on the bottom of the fraction on the left? What do you learn about fractions when you have the same thing on the top and the bottom? And lo and behold, Sierra, I end up with this. The velocity of the second can, the heavier can, is equal to negative, the opposite direction, velocity of the first can over 2. Sierra, my angel, can you read to me this line up here? Stop. That's this one. Keep going. Half as fast divided by 2 of the first. There's a purely algebraic proof. We're done momentum. I'm going to give you some homework. Next class is going to be a take-home quiz. You can do number 1. Okay. Number 2, now if you look at these pictures, if they're touching like that, you can assume they're stuck together. What's the initial what's the initial velocity of the 2 kilogram mass? 5.2. What's the initial velocity of the 13 if I don't put a velocity there? You can assume it's at rest. Okay? So these are a bunch of little pictures. Here we have 2 moving to the right and they stick together. Here we have 2 moving to the right and they stick together as well, but with different velocities. Here, 2 moving to the right and they don't stick together. Turn the page. Here, a little head-on collision. Okay. 3 is good. 5 is good. Christian, you play football?
Yeah.
Christian, you play football?
Yeah.
Then we have to do number 6, all of us. Eight is good. 9, 10. You can put a star next to number 12. This would be an example of a nasty multiple choice. I don't think I'd make this a written, but okay. 12 is fair game. There's a mu, so this is some good practice of review. We're getting towards the end of the year. We'll pause there, I think. 13 is cool, but I'll leave that alone. Okay.